So if you have a matrix, a 2 by 2 matrix, A, B, C, D, what is the determinant of this matrix? A times D minus C times B or B times C, right? So it's this and that. We've done that when we're doing cross products. We've had to do a bunch of determinants, haven't we? Okay. Let's see if we can't rewrite this as like the determinant. So I should write this. The determinant of that matrix is this, right? The determinant of that matrix is this. Can you rewrite this as the determinant of a matrix?
Yeah.
How? D what? Say again. D. Are you saying D dx like that?
dx over d.
I guess I'm just partial x.
Oh, okay, okay. Partial. All right. Partial x with respect to u, and then here partial y with respect to v, and then here. It doesn't matter, or does it? Should we put it in order? Do you want to put maybe the y down here, and then the x up here? So then your x's are on top, your y's are on the bottom, right? So you're doing, it's like you're doing partial of x with respect to u, partial of x with respect to v, partial of y with respect to u, partial of y with respect to v. And then when you do this determinant, you get the inside of that, right? Okay. All right. Why is it again we can't use this formula right now if I want to talk about spherical? Yeah, this is what we did when we had two-dimensional, right? A double integral. If we go to triple, then we need a third conversion, right? X goes to something, y goes to something, z goes to something. So let me ask you this. Do you know what the determinant of a 3 by 3 matrix is? A, B, C, D, E, F, G, H, I, J. How do you find the determinant of a 3 by 3 matrix? I know some of you have done this.
I remember learning about this, but I'm trying to remember. I know how easily you plug in the calculator.
All right, Brenda, do you have a way?
Well, there's like an equation, or you can like take the determinant of like a smaller square and the.
Yeah. Okay. So, how many of y'all have seen that? How many of you have seen the determinant of a 3 by 3 before? You have? Okay. How many of you remember being taught that determinant by using just a formula? Like there's a formula for it? Okay. I think our book just uses a formula. Hold on. Let me double check what the book has. I don't even know where they cover this. I think it's in this section though. Hold on. Okay, so I don't even see that they do this. Hold on, let me see if they do. Well, I'm trying to just bear with me for a moment. I want to see what they're doing here. Okay. Okay. They don't show it. I think they just assume you know it's from somewhere.
They don't specify where, just somewhere.
So does anyone want to share? Brenda, do you want to walk? If I'm not putting you on the spot, okay? But do you recall at all what you do?
Yeah, I took linear algebra like not last semester.
Okay.
The semester before that.
So here's what we can do. Again, there's different ways it's shown, okay? Here's what you can do. we are going to compute the determinant of this by first separating this top row from the bottom two rows, all right? And what we do is we're going to start with this right here, A. Okay, so I'm gonna be working with A. I'm gonna put A times, now since I've looked at this A, I'm going to cover up this column and cover up that row. And you see that right there?
Yes.
What, the little 2 by 2 that's left?
Yes.
We want the determinant of that. Okay? That will be next to this. So I'm gonna write it this way. I'm gonna put bars on it. F, G, I, J. So these bars right now are gonna mean the determinant. Okay? So I do A, cover this up, determinant of what's left.
Yes.
Then I do minus B times, now I cover up B and the top row, and you see those four.
Yes.
I want the determinant of those. So E, G, H, J. Okay? And then one more. I go to C, and this will be plus. Plus C, determinant of what? EF, HI. Now remember, this is a determinant, this is a determinant, this is a determinant. You have to do those. All right? Yeah. Yeah, that's where you go like this and that. Okay. So let me ask you now, what if you had the determinant of A, 1, 1, A, 1, 2, A, 1, 3, A, 1, 4, A, 2, 1, A, oh, that's not A, 2, 2, A, 2, 3, A, 2, 4, A, 3, 1, A, 3, 2, A, 3, 3, A, 3, 4, last one, A, 4, 1, A, 4, 2, A, 4, 3, A, 4, 4. Okay, what if we want to do a determinant of a 4 by 4 matrix?
Basically, what you do is you take the first variable in the top corner.
Okay, so top corner A11,
Yes.
and you multiply that times what? The determinant of covering and covering. That's going to be a 3 by 3.
Yeah.
So this one would be the A22, it would be this one, right?
Yeah.
That would go here.
Yeah.
And what's the formula for that one? This one, right? And then you would say minus, the next one would be A12, and then another determinant. So you cover this up, and it would be the determinant of those three. And that's a big monster, right? And then the next one would be plus, blah, blah, blah. Next one would be minus, blah, blah, blah. And you can get a general formula for this. So if you go to 5 by 5, then you're going to have first one, and then you're doing the determinant of a 4 by 4, which is really the determinant, couple of determinants of 3 by 3s, which is really a couple of 2 by 2s. Becomes pretty ugly. All right, now, with all that said, and going back to this idea right here, when we made our conversion, x became, or our change of variables, x became a function of u and v, y became a function of u and v, then what we wound up doing was taking the determinant of this thing, right? That's what the Jacobian determinant we had to stick into the integral was. So if we go into a conversion that involves 3 variables, so x becomes some function of, let's say, u, v, and w, y becomes some function of u, v, and w, and z becomes some function of u, v, and w, then the Jacobian is going to be the determinant of what? So look at this format. What do you think this is? This was partial x with respect to u, partial x with respect to v, y with respect to u, y with respect to v. So what do you think our first row is going to be here? X with respect to u, x with respect to v, x with respect to w. What would the next row be? Y with respect to U, Y with respect to V, Y with respect to W. And then the last row, Z with respect to U, Z with respect to, what the hell am I doing? V, and then Z with respect to W, right? And then to do that determinant, we would do that times the determinant of those, minus that times the determinant of these, plus that times the determinant of those, right?
Right.
Okay. My marker's dying. But we're not. We're going to stick this out. Okay, you ready to see spherical now? Okay, so here's spherical. Not happening with that marker. Okay, for spherical, just to make it a little bit like what we've seen, x is turning into actually a function of what? Rho, theta and phi, right? Doesn't matter how I write those. And then y is becoming some function of rho, theta, or phi and theta. And then z is becoming some function of rho, phi, and theta, right? That marker's not going to go. Let's see here. Maybe. So how would we change this if we were going to do it this way? What were they? Sorry. X went to what? The actual conversion was cosine, theta, sine, phi, right? What was it for this one? Rho, sine theta, sine phi, and then the last one was rho, cosine phi. Right? Those are the actual conversions. So on this right here, this table we have, we want to use this, right? But we're not using UVW. What are we using? Rho. Okay, so I'm just going to come in here because I can erase quickly. I'm going to change these. Are y'all getting this, or am I off on my own right now? Am I in my own little world? Kinda?
Makes sense.
Okay. Here, 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 here. Oh, it's not even much yet. Wait till we do this calculation. I've only done this a few times in class because there's so many places you can mess this up, all right? So wish me luck. I'll be happy if we get it. I know it works, but it's just, is it going to work today? Okay. This one looks pretty good. That one. All right, you ready for this? You ready? Okay, we need to take the absolute value of the determinant of that. Okay, here it comes. So the determinant of that is equal to, so this, and I'll take the absolute value at the very end. Oh, absolute value is going to be absolute value of, okay. Remember what we're doing? We're doing this first, right? This, do you want me to actually write down partial of x with respect to rho times the determinant, or can I just start doing this mentally? You want to
mentally?
Do it mentally? Okay, so what is the partial of x with respect to rho?
Which is partial of 1.
Partial of this with respect to rho is just cosine theta sine phi, right? Okay, that's the first part. Then I have to do that times the determinant of this piece right here, right? Okay, so let's do these. I'm not going to do the determinant, I'm just going to calculate each of these. What's the partial of y with respect to phi? So rho sine theta cosine phi, right? Right, so rho sine theta cosine phi. You with me? Okay, that's just that. And then this one over here, partial y with respect to theta, which is rho partial of y with respect to theta Rho cosine theta sine phi. Okay, and then I need this piece, partial of z with respect to phi, negative rho sine phi. And then this one, partial of z with respect to theta. There's no theta. 0. Yes? We've just begun, right? That takes care of this times that determinant. Now I have to say minus I might have to start writing smaller here. Minus, now I'm working on this one, right? So let me take this out, take that out. So I'm working on this one. And since I'm working on that, I'm going to be doing the determinant of this one with this one, right? Those two? Okay, so minus, what's the partial of x with respect to phi? Rho cosine theta cosine phi. So rho cosine theta cosine phi. Determinant of partial y with respect to rho. Y with respect to rho, sine theta sine phi. Okay. Let me do the one below it. Partial of z with respect to rho. Cosine phi. Okay, do this one. Partial y with respect to theta. Rho cosine theta sine phi. Rho cosine theta sine phi. Please pay attention, because if I screw one thing up, it's over. Partial of z with respect to theta, 0. Okay, 2/3 of the way there. Then we have to calculate the determinants. Then we have to clean it all up. And at the end of it, it's supposed to be rho squared sine phi. Yeah. Okay, so I'm going to erase this part. I can maybe squeeze this in here. I'm going to do plus, right? Now I'm moved to this part, and I'm here now, right?
Yeah.
So partial of x with respect to theta is negative, isn't it?
Yeah.
So I'm going to change that now to a minus. Minus rho sine theta sine phi. Determinant, partial y with respect to rho. Sine theta sine phi. Shit, I'm out of room. You know what I'll do? Rho cosine theta sine phi. Rho sine theta sine phi. Rho cosine phi. Okay. All right. So there we go. That's what part am I on? There. I did that, right? Yeah. Let's do y with respect to phi. Y with respect to phi is this one, so that's going to be rho sine theta cosine phi. Almost there, almost there. Partial of z with respect to rho cosine phi. And finally, partial of z with respect to phi. Negative rho sine phi. All right. Yay. Setup is done. And then, yeah, we'll want the absolute value of all this when we're said and done. Let's do some determinants now, some 2x2 determinants. So this should be an absolute value here, and then we should have another one way down here. All right, we have cosine theta sine phi times, let's do this determinant. Oh, this one's nice, right? 0, and then minus this times this, but that's a negative, so plus, right?
Rho squared cosine theta and sine
Cosine theta sine squared phi. And there's only one term there, right? There's only one term from that.
Yes.
Excellent. Okay. Now, minus rho cosine theta cosine phi. And then another nice one, right? This is gone. And then this one is...
rho cosine theta cosine phi sine phi.
And it'll be minus, right?
Yeah.
Minus rho cosine theta sine phi cosine phi. Okay, and that's going to be multiplication, so those two negatives are going to become a plus. finally, minus rho sine theta sine phi. And unfortunately, there's not a 0 in this one. So here to here, we've got minus rho sine theta sine squared phi. And then minus this, right? So minus rho sine theta cosine squared phi. Yes. All right, let's take care of a couple of basic stuff first. Okay, that minus and that minus become a plus, right?
Yeah.
Okay, I can factor a negative out of both of these and bring it out and make that a plus. I like what I'm seeing here. Do y'all see what I see here? I have a rho sine theta, in both of these. I can factor that out, and I'll be left with sine squared phi plus cosine squared phi, which is 1. So this will become plus rho sine theta sine phi. I pulled out a rho sine theta, and then the rest of it went to 1. But this is just rho squared sine squared theta sine phi. Yes?
Yeah.
Okay, let's go down here. See if there's anything going on down here. Okay, down here, let me just clean this up. This is rho squared, because these are being multiplied, right? Cosine squared theta sine cubed phi, right? Okay, plus, let's see, that takes care of that. I've already taken care of this. Okay, that one, I'm just going to multiply again, right? Just multiply that together. So I've got a rho squared, cosine squared again, cosine squared theta. So I took care of rho, cosine theta. I've got a cosine squared phi, and I've also got a sine phi just kind of sitting there, don't I? Okay, let me take that, let me just bring it down here because it's too far away from me. Rho squared sine squared theta sine phi. Okay. Any suggestions? You can pull rho squared out of everything, right? Well, that's nice because if I pull rho squared out of everything, my answer is supposed to have rho squared in it, right? So rho squared is out. Let me just pull that, pull that, pull that. Now in parentheses here, this better turn into sine phi. So anyone see what I can do?
Honestly, I would see. I mean, you could.
Do they all have something in common? They all have a sine phi, right?
Yeah.
Let me pull that out. I'm going to put it back here because I don't have room up front. Sine phi comes out, then this is gone, right? That's gone. And this is now squared.
Yes.
What about those two? What can I pull out of those two? A cosine squared theta. What happens if I pull a cosine squared theta out of both of these? I'll be left with sine squared phi plus cosine squared phi, right? Which is 1. So just this together becomes cosine squared theta, doesn't it?
Yes.
And what did I still have down there? Sine squared theta. And that becomes 1. So all this in here becomes a 1. So you're left with rho squared sine phi. And that's why when you go from Cartesian to spherical, you have to include the rho squared sine phi, because the Jacobian determinant tells you. But the conversion, the actual conversion, x equals rho cosine theta sine phi, that conversion, that change of variables it made sense. This change of variables takes us from Cartesian to this thing called spherical, which visually we can understand. But there's nothing stopping you at all, okay, from saying, hey, look, I'm just going to replace x with u squared plus v squared minus w squared. I could just decide to change my variable to this. And every time I see, every x gets switched to this, every y would get switched to something else, every z would get switched to something else. Now I've got 3 new variables, right? And I can change my integral over, but I've got to include the Jacobian determinant. All right? Wow, okay, that was, like I said, I usually don't go down that road, but it's nice to see it. Plus, we got to bring up determinants of 3 by 3 matrices, which doesn't come up all the time. That was somewhat exhausting. All right, let's take a deep breath. Okay, that's it. Now, we are going to do this example. We have about, what, 20 minutes, 22 minutes? Let's see how this goes. All right, so in this problem, you are being instructed to make a change of variables. They're saying, look, everywhere there's an x, you're going to replace it with 1/4 u plus v. Everywhere you see a y, you replace it with 1/4 v minus 3u. And then they want you to evaluate this double integral over d of 4x plus 8y dA, where d is this parallelogram. So what I'd like to do first is draw d in the xy plane. So what does d look like? All right, well, it's this, right? So let me go. -1, 3 is up here. 1, -3 is down here. 3, -1 is here. And 5, 1, or sorry, 1, 5 is, that was 3, is up here like that. Is that right? 1, 5. Now, we could try to do this double integral over this region D, because that region D, we could probably break it down into maybe like two different integrals, like right down the middle there, and like treat this left side like a type 1, where you have an upper function and lower function, and the right side where you have an upper and lower. So we could probably split this up, right? But somehow this change of variables is going to do something better. Maybe, all right? Let's see. So let's see what happens here through this transformation. So what actually happens when we do this transformation? Well, let's just take a look at what happens to these points. So what would happen to that point right there? That's the point -1, 3, right? Let's see what would happen if we transform this point through this transformation, this change of variables. What would that look like in the new domain? The new domain switches us from x and y to u and v, right? So how would we figure out what that point -1, 3 does? Well, look at these equations, right? This is x, this is y, right? So what would happen if I go to those equations? So right now I'm going to look. What happens to the point -1, 3? Well, that would mean that this equation has to be equal to what? -1 has to be equal to 1/4 u plus v. And then what would the other equation have to be? 3. So, and 3 would be have to equal 1/4 v minus 3u. All right, so let's see what goes on here. Let's multiply both sides by 4 here. We get -4 equals u plus v. And if we multiply both sides by 4 there, we get 12 equals, I'm going to go -3u plus v. And what do I have now? Two equations, two unknowns, right? System of equations, linear equations. So you can kind of choose how you solve these. I think I'll do a matrix over here, our system of equations. I'm going to do u plus v equals -4, and the other one is -3u plus v is 12. Are y'all following what I'm doing?
Yeah.
Okay, so now I'm going to multiply this. I'm going to choose to multiply this first one by -1. That'll make that negative. I'll make that negative, and that'll make that positive. And then I can add them straight down. So I'm doing elimination. What do I get if I add straight down here? -4u equals 16. So u would be -4, right? Once I know what u is, I can go back and get v. So if that's -4, then what's v? 0. Is there a question or no? Explaining? Okay. So that means this point, -1, 3, went to the point, where? -4, 0. Over here, u is -4, and v is 0. So it went to that point, right? All right. We have to do this for all 4 points, and it's going to be a little time consuming, right? So let's try, maybe we can go a little faster through the next one. What would happen if I change this? Let me go to this one right here. If this was changed to a 1, and that one's changed to a negative, how would that change that? This would be 1, and this would be 4, right? And this would be negative, and this would be negative. And then up here, I know I'm going through this fast. I'm sorry. I apologize. This would have been plus, and this would have been minus, right? Nothing else changes? So now we multiply through by negative again, right? Add down, and you get -4u equals -16. So u is 4. And if u is 4, you can come back and get v is 0. So now what you get is this, 4, 0. Okay? Now, these 2 points, where was 1, -3? 1, -3 was here?
Yeah.
Here's the great thing about this transformation, is that if these 2 points are connected here, right, with a straight line, see how they're connected with a straight line? And our transformations are linear. See how these are linear? U, v, these are not squared or anything like that. If these are linear transformations, then line segments go to line segments. So this line segment here that connects these 2 points should be transformed into a line segment that connects those 2 points. So basically this line, I'll call it L1, is actually this line right here, from here to here. All right? Then we can do the same thing for these 2 points. So let's see, that point is the point 1, 5, and this is the point 3, -1. So we have to play this game again, all right? Unfortunately, I got to keep doing this again. Okay, let's do it. Let's do the one for 5, 1, or 1, 5, sorry. For 1, 5, this equation becomes 1 equals 1/4 u plus v. And then the other one becomes 5 equals 1/4 v minus 3u. This is tedious, yes?
Yeah. Yes.
Okay. 4 equals u plus v. Do this one a little different because I know I'm going to go to a system. This one is 20 equals -3 u plus v is 20. So replacing that, solving or clearing out the fraction. Multiply by negative again. Negative, 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 add down. -4u equals 16. So -4u equals 16. And so u is -4. Right? If u is -4, then what's v? It's a little different this time. If u is -4, plug it in right here. -u minus v equals -4. If u is -4, it's -4. minus v equals negative 4. So v is 8. You wind up getting v is 8. What was u? U is negative 4. V is 8. So u is negative 4. V is 8. With me? Okay. Now, these 2 points should be connected because, remember, this was the first point we did, right? And that was this one. And that point connected to there through a linear transformation, that line should connect, so this should go here, like that. And then we do the next one. And the next one, I believe, I'm not going to go through the work, okay? But I believe the next one is going to be this one right here. And so what happens is you wind up, through this transformation, you have taken yourself from a region which is not necessarily easy to do, right, to a rectangle. And you can do this very easily because your limits of integration will be constants, right? U will go from negative 4 to 4. V will go from 0 to 8. So your double integral is nice. But there's one catch. We still need to do something. We still need to do the Jacobian determinant, right? So can we do the Jacobian on this? What would the Jacobian determinant be? I know, I'm not selling you on this, am I? You're like, shit, I would have already done it the other way by now, right? Okay, so what's the Jacobian? I'm going to call it capital J. That would be, we need to do, remind you, it's partial x with respect to u, partial x with respect to v, partial y with respect to u, partial y with respect to v, and then we do the determinant, right? So what is the partial of x with respect to u? So remember, this is x, right? Remember, the 1/4 would just go through both, right? So this is just going to be 1/4. What's the partial of x with respect to v? We would have 1/4 and 1/4. So wouldn't we again get 1/4?
Yes.
Okay, what's the partial of y with respect to u? So be careful. Partial of y with respect to u, we're doing derivative of that, negative 3/4.
Yeah.
Okay. And then what is the partial of y with respect to v? 1/4. Okay, now the Jacobian of this. So here, 1/16 minus negative 3/16. Ooh, right? Which is going to be 4/16, 1/4. So our Jacobian, that piece that we need to put in there is actually a constant in this case. That happens anytime your transformations are linear, you're always going to have a constant there. Last step, let's set up the double integral. This double integral right here, ready? Becomes integral from negative 4 to 4, integral 0 to 8. So these are my restrictions on u, v. Okay, 4 times x. But what's x? It's this. So 4 times that would just be u plus v, wouldn't it?
Yes.
So this is going to be u plus v, and then plus 8 times y. 8 times that would give you 2v minus 6u. And then we're going to do all of that times 1/4. That's the Jacobian, right? That's this. And then we have dv, because v went from 0 to du. And those will be pretty easy to do. Like we can just pull the 4th out if we want. This will be what, like 3v minus 5u? And that'll be easy to integrate. So you might look at that right now and you just be like, yeah, right. I would have done that another way, right? Yeah? So what's the value of something like this then, right? Not only that, but I gave you the transformation. I told you, hey, use this transformation, right? Like this is supposed to make our lives easier. Wouldn't you agree? I'm not sold. Are you sold? No? Okay, until I give you this problem. Now I'm going to sell you on it. Okay, here's the problem with this one. It's not the region of integration that's the problem. It's the integral itself. you are going to have massive problems integrating that with respect to x or y. Either way, you're going to have a problem. I'll convince you of that by asking my computer to do it. I'm going to ask my computer just to try to give me just the general antiderivative. I'm just going to go with an inner integral of, oh, I'm not ready for that. Oops. Screwing things up. Of exponential raised to the, I've erased it. What was it? X plus, let me just look at it one more time. X plus y over x minus y. X plus y over x minus y. And do you care which one I go with respect to first? You want me to just you want to try y first? Uh-oh. Here we go. It's bringing in the exponential integral error formula, basically. Not good. Not good. And so if I try it with respect to x, we're going to have the identical problem because it's just not something, it's because the variable here is appearing in the top and bottom. It's just, we're no go, all right? We're dead in the water here pretty much. So is there a way that we can handle this? Well, the problem with that integration is that the x is appearing both on the top and the bottom, or the y is in the top and the bottom. Do you all agree with that as being the problem? It'd be nice if the x's were on top and the y's were separated, then that would be nice. So I'm going to come up with a transformation now. Watch the transformation I'm going to use. I'm just going to let u be x plus y, and I'm going to let v be x minus y. If I do that, then this new double integral will become the double integral over some region S. I'm not quite sure what it's going to be yet, but it'll become e to the u over v. Then I'll have a Jacobian in here, right? Which I'm going to have to figure out. And then I'll be able to do like, you know, dv du, or maybe du dv. I'm not sure about that order yet. Do you all understand? Yeah. Now, if I have to integrate this with respect to u, I can handle it. Can you handle it? If you have to do it with respect to v, you can handle it. Because they're separated, so you should be able to work with those. So do you see how this could be valuable? Now it's just a matter of determining, like, what does this region transformed over look like? And not only what does it look like, what's my Jacobian? Now there's a problem here, because this, I made a substitution, u is x plus y and v is x minus y. I actually need these written another way. I need these written x as some function of u and v, and y as some function of u and v. Right now, u is a function of x and y, and v is a function of x and y. I need it reversed. Does that make sense? Okay, so what do y'all want to do first? Y'all want to go after the Jacobian, or you want to do the region, or you just want to call it a day? Never mind, we'll do one of the first two options. Let's go for Jacobian first, okay? Jacobian first? Okay, for Jacobian, we have to somehow make these look like x equals something with u and v and y equals something with u and v. How can we do that? How about we solve this one for x? Okay, take that, solve it for x. You get x is equal to u minus y, okay? Now take this one and solve it for y. Yes? Solve it for y? What would you get? Y equals x minus v. Okay, maybe what we can do now is we can write this one that has x in it, right? X equals u minus y. Replace that y with this. So what would that one become? U minus parentheses, what is y? X minus v. And that we should be able to clean up, right? This is going to give us x equals u minus x plus v. And I can move the x's to one side, so I get 2x equals u plus v. And voila, I have it. I have that x is equal to half of u plus v. Now how do I get y? Same sort of story, except I can go a little bit faster now because I have y is equal to x minus v, right? And I know what x is. So I can take that one. I go y is equal to x, 1/2 u plus 1/2 v. I'll distribute now. And then minus v, which is 1/2 u minus 1/2 v, which is 1/2 u minus v. Just factoring out the half. So there we go. We have our two transformations. This one was 1/2 u plus v. This one was 1/2 u minus v. These transformations are linear, which means that if these are line segments, which they are, it's going to get transferred over to line segments. That's beautiful. We want that, okay? Because if these are nonlinear transformations, it's much more difficult problem. Much, much more difficult. Not much more, just much more. All right, Jacobian. Let's do Jacobian. Okay, the Jacobian should be partial x with respect to u, partial x with respect to v, partial y with respect to u, partial y with respect to v, which is partial of x with respect to u, partial x with respect to u, 1/2, partial x with respect to v, half again, partial y with respect to u, 1/2, and then minus 1/2. Now we do our thing. So negative 1/4. Sorry, I'm supposed to, well, I'll just leave it like this. Okay, negative 1/4, and then, so negative 1/4, and then we're subtracting 1/4 again. So this is minus 1/2. Now we're supposed to put the absolute value of the Jacobian in the integral. So we're going to throw 1/2 in, aren't we? I've got good news. I've got good news. I've got good news. All right, here's my good news. Take a quick look at the picture of the region in the xy. 1, 0. 2, 0. 0, negative 2. 0, negative 1. Not that pretty, right? But, I mean, it's not terrible. So we wouldn't be scared of this. We're scared of the integral. Okay, so this, though, let's start moving some points over. So my original transformation, not transformation, substitutions were x plus y for that, and v was x minus y, right? Those are my substitutions. So check this out. If we use the point 1, 0, right? Then we can go straight, this is x, this is y, right? Yeah. We can go straight to u and v from this. Look, if x is 1 and y is 0, what's u? U is 1. And if x is 1 and y is 0, what's v? 1, right? So the point 0, 0 in the xy plane is going to go to the point 1, 1 in the uv plane. Okay, so that's that one. Now let's go 2, 0. Are those two connected? 1, 0 and 2, 0. So we're going from here to here, right? Those two?
Yeah.
So if I do that one, 2, 0, where does that go to? So 2 here and 0, so we get 2, 2. So that goes to the point 2, 2 here, and I know those are connected with a straight line. And I keep going. How about 0, negative 2? That goes to, so if I plug in 0 here and negative 2 here, right? I get negative 2 for u, and what do I get for v? Positive 2. So that puts me at negative 2, positive 2. And are those connected? What's connected here? I just went from 2, 0 to 0, negative 2. It's these two, right? So from there to there was this one, connected to that one, so that goes there, like that. And then, let's go, where are we? This one? 0, -1. So that's going to go, should be -1, 1, right?
Yes.
So -1, 1 goes here. Those two are connected, and that connects back. So we went from a trapezoid to a trapezoid. So you would say, what are you doing? You're crazy, right? You're a crazy person. But the good thing is we can integrate this now, right? This we could still handle, but now we can do the double integral. So final setup here. We're going to do, watch this, okay? You ready? So that is your Jacobian, okay? Okay. Hold on, let me think. What's that?
Yeah.
So I'm looking at this as a type 2 region. I'm going this way with it. Okay? So what are my U's stuck between? My V's are stuck between what? 1 and 2. So I'm going to be doing dV on the outside. The inner integral will be du. So what are my restrictions left and right? This has the equation v equals u, but I need to solve it for u. So u equals v. This one has the equation v equals -u, so I need to solve that for u, so I get -v. Left bound, right bound. Okay, what's the integrand? E to the u over v. And I already have the 1/2, that's it. I'm done. I'm done. I'm done with this chapter. We are done with this chapter. All right, so what's going on for next week? We have nothing due on Monday, right? And we're officially done with chapter 12. Well, I'm done. You're not done. You should have a lot to do in chapter 12. The next mini exam, does anyone have the next one with them by chance? Can I take a look real quick? Just want to see what I'm sending you home with. Oh, I'll give you a hint. On number 1, hold on. No, okay, on number 1, I give you a formula and then I just ask you to apply it, so you can do that. Number 2, use spherical coordinates. And number 3 is a change of variables. Oh, wow. So number 3 on the mini exam is exactly like this one. Well, not exactly, but pretty close. Remember, what I was trying to do here was to make this easier, right? So I just chose something for that and it worked. On the mini exam, you'll have to choose something, and I think it's going to be pretty clear what to choose, and it'll work, all right? Yeah, so you officially have everything you need to finish that next mini exam. Have a great weekend, okay? What?
No.
Oh, okay.
I hate working.